Hello, and welcome to section 5.5, the substitution rule. In this section, we're going to see how to turn more complicated integrals that we don't know how to find the antiderivative of into simpler integrals where we do know how to find the antiderivative. And we've used the method of substitution in other forms in the past in algebra. So if you think back to an equation like this. So we don't know how to solve that as is, but we can recognize that as a quadratic form. So here you have e to the x is squared, here you have 3e to the x, and here you have a constant. So we could make a substitution. You could say let u equal e to the x. Then you can rewrite this in terms of u. It's a quadratic in terms of u. And you can solve it because you know how to solve a quadratic equation. Then you make your substitutions back, so you replace u with e to the x in your solutions, and then you solve for x. So that's the type of thing we're going to be doing here. But it's a little more complicated because integration is a little more complicated than solving an equation from algebra. We're also going to refer back to the differential. So let's look at an example. Here's a simple example, the indefinite integral of the cosine of pi over 2t. So this is not simply equal to the sine of pi over 2t because you have a composite function, right? And when you take the derivative of sine of pi over 2t, it should equal this. But I know that using the chain rule, the sine of pi over 2t is going to be pi over 2 times the cosine of pi over 2t. Remember, the derivative of the inside times the derivative of the outside. So I need to do more work, but that is a good place to start. Let's make like we did with our algebraic example where we found a piece of the equation and we simplified it by setting u equal to that. Let's do the same thing here. With our composite function, let's set u equal to this inside function, pi over 2t. So if u is equal to pi over 2t, then my integrand turns into just cosine u, and I know how to find the antiderivative of that. But that means I'm turning that whole integral into something in terms of u. So we can't forget the du, right? That's the differential that's always tacked on to the end of the integral. So let's take a step back and look at what we're doing. So if we're saying that I'm going to make a substitution, and because the antiderivative of cosine u is sine u, what happens when I find the derivative of sine u with respect to u? Well, it's the derivative of the outside function, which would be cosine, evaluated at the inside function, which is pi over 2t, times the derivative of the inside function, which is pi over 2. So I see that just saying replacing pi over 2t with u is giving me an extra factor of pi over 2 when I find the derivative of sine u. So I need to do a little bit more work. So this is where the differential comes in again. So that dt that we've seen tacked on here is actually a differential. And if we think of our substitute variable here, our substitute function u, du, the differential of u, is just the derivative of u of t, which is pi over 2 dt. So remember, I need to get my entire integral in terms of u, not t, so that I can find the antiderivative and simplify things. So if we let u equal pi over 2t, then du is pi over 2 dt. That's that differential. So now I can simply solve for dt to get it in terms of du, and now I can make the substitution for every part of my integral. I have the cosine of pi over 2t times dt equals, if I substitute u everywhere I see pi over 2t, I get cosine u. If I substitute 2 over pi du everywhere I see dt, I end up with this simplified integral. And this I know how to find the antiderivative of. So this is simply 2 over pi sine of u plus c. And then if I put it back in terms of the original variable t, it's 2 over pi sine of pi over 2t. So what we did here was made sure we replaced every part of the original integral to make it in terms of the new variable. So we can't just look at the function. We also need to look at that differential and get the new differential in terms of the old, or the old differential in terms of the new, depending on how you look at it. So this, being able to do this with the substitution rule, what you're really doing is you're transforming your integrand into the result of using the chain rule on a composite function. So oftentimes what you want to do, like we did in this last example, was look for the inside function to be your substitute u, your substitute function, and then get the function that you're finding the integral of and the differential in terms of this new variable u. So lots of examples, really the best way to get your head around it. So let's look at this example. Unlike the last example, this is not an obvious composite function itself given in the integrand. So, but what you want to do is look for parts of the integrand to make your substitution with. And in particular, you want to look for what part of this integrand is a derivative of another part, of another factor. So if you look at the denominator, x to the fourth minus 5, the derivative of that, of x to the fourth, is x cubed. So if I make this my new u of x, my new function, its differential is the derivative of this function times dx. So I'm going to say, all right, let u equal this denominator, x to the fourth minus 5. The differential, du, is 4x cubed dx. So that's good because I can get rid of that 4 by just dividing both sides by 4. So I can replace x cubed dx in my original integral with 1/4 du. And then I can replace x to the fourth minus 5 with just u. So this integral simplifies to 1/4 times the integral of du over u. And that we know how to find the antiderivative of. That is 1/4 ln of u plus c. So putting it back in terms of x, I get 1/4 ln of x to the fourth minus 5 plus c. So notice that my outside function was actually 1 over u, and my inside function was my substitution, x to the fourth minus 5. So this example is showing us, you don't expect to always be given an obvious composite function. Sometimes you need to just look for different parts of the function and try that as your substitution, and then find the differential of that function, of that u. Here's an example where you do have kind of an obvious case. So I have a power of cosine, and I know that the derivative of cosine is minus sine. So this is an easier example to see. This is more obvious. So if I let u equals cosine theta, that's the inside function if you think of this as the outside function being cubed, u cubed. So if my inside function is cosine, that u equals cosine theta, then I need to find the differential. Du equals the derivative of cosine theta, d theta. So I can solve for this sine theta d theta factor by just replacing it with minus du. And then I replace cosine cubed theta with u cubed. So replacing all those parts in my integral gives me this. And I know how to find the antiderivative of that. It's minus u to the 4th over 4 plus c. And then I substitute back because I want to get my answer in terms of theta again, not u. So notice that in those last two examples, the differential du in terms of the new variable was always a constant multiple of the differential of the original variable. But here's an example where it's not. So we have x times the square root of x plus 2 dx. So we have a composite function in this factor, but the whole thing again is not a composite function. So you know, u's always been in what the examples we've had up to now, the inside function's always been a good candidate for u. So for this factor, let's try u equals x plus 2. Then we simply have du equals dx. But that's not sufficient because we still have this x factor here to the left of our square root. But notice that if we solve for x in our expression for u here, I get x equals u minus 2. So what happens if I replace this x with u minus 2? I get u minus 2 times the square root of u, which is u to the 1/2, du. And now that is easier to work with because I just have powers. So I'm multiplying that through, I have u to the 3/2 minus 2u to the 1/2 du. And I know how to find the antiderivative of this, right? Turn it into the sum and take the sum of the antiderivatives. Then I'll put it back in terms of x. So replace that u with this quantity x plus 2. And we're done. So in this case, my words fell off the bottom of the screen here. But in this case, I didn't have my differential as a constant multiple of the original differential. But I was still able to, replace every factor, every part of my original integrand in terms of u, and I still got an easier integral that I know how to find the antiderivative of in terms of u. Here's another example that looks really scary, but it's not, because look at each part of the function. So if you look at arctangent, if we let u equal arctangent x, we need to find the differential. Then du is the derivative of arctangent, which is 1 over x squared plus 1 times dx. But look what those other parts of our integral are. So that's perfect. So really, I can put this in terms of u. I have the integral of u squared, and then this dx over x squared plus 1 is just my du. So this is simply u cubed over 3. This integral sign should not be there. This is u cubed over 3 plus c, and then I put it back in terms of x. And I get 1/3 arctangent cubed plus c. Here's another example. It's a little more complicated. So again, we've had good luck with whenever we have an inside function letting that be u. So let's try that. So if we let u equal x squared plus 1, then how do we find dx? Well, how do we find du? Du is 2x dx, right? So then I would have u to the 1/2 replaces this square root. I have 2x dx is equal to du, which means 1/2 du is equal to x dx. But I have x cubed dx here. I don't have x dx only. So I need to do a little more work. So we have that factor of x cubed. So again, look back at what you said was u. So if we solve this for x, we get x squared equals u minus 1. And that works out because I have this factor of x here from my expression for du. And then since x times x squared is x cubed, I can replace that x squared with u minus 1. X cubed dx is going to be u minus 1 times du over 2. And then the square root of x squared plus 1 is going to be simply square root of u. So I can turn that into the integral of sums of powers and use the power rule on each of those. And then putting it back in terms of x, this is my solution. So there's another example where it's not just a constant multiple. The differential in terms of u is not just a constant multiple of the differential in terms of x. So, but then you look back at your original substitution and see what you can do so that all factors in your integrand are replaced in terms of u. So up to now we've just been looking at indefinite integrals. So you can also use the substitution rule for definite integrals, and obviously because you have the same process up until you evaluate it at the limits of integration. But one thing that you can do is, if you want, since a definite integral evaluates to a number, you can evaluate your the antiderivative in terms of u. You can evaluate it at the inside function, evaluate it at your original limits of integration. So it's easier to just show an example. So here I have sine of t over cosine squared t, and my limits of integration are 0 and pi over 6. So again, I can recognize that I have a composite function here of cosine squared t, and the if I let u be cosine t, then du is sine t dt. Excuse me, minus sine t dt. So I know that my substitution is going to be u equals cosine t. So then du is minus sine t dt. And then what I can do is change these limits of integration to be in terms of u as well. So when t is pi over 6, I'm going to evaluate my new, using my substitution to get a new limit of integration. So then u equals cosine pi over 6, which is the square root of 3 over 2. So I'm going to replace this upper limit with square root of 3 over 2. And likewise, I'm going to take that lower limit and I'm going to put that into my substitution. And the cosine of 0 is 1. So I'm going to replace this limit, the lower limit, with 1. So here's my original integral, definite integral. Here I'm replacing everything with in terms of u, including the limits of integration. So notice that, remember that the negative definite integral from a to b is equal to the definite integral from b to a. So I'm just getting rid of that negative sign and switching the upper and lower limit of integration. So this is u to the minus second du. I find the antiderivative and I evaluate it at these new limits of integration that I've gotten from my substitution. So at this point, we could have substituted back so that our antiderivative was minus 1 over cosine t. and then evaluate it at the original limits. But that's an extra step that you don't really need to do. Oftentimes it's easier to just find the new limits of integration and evaluate your antiderivative in terms of u. So another thing that helps with integrals that you don't know how to find the antiderivative of is to recognize when the integrand is an odd function. And you can use symmetry to solve it. So remember that an odd function is symmetric about the origin. So that we've seen this before when we looked at Riemann sums. If you have an odd function on an interval such as like -2 to 2, where you have it ends at the negative, so 2 is the opposite of -2, because the height of the rectangles here are negative values, yet they're the opposite of the height of the rectangles here. We saw that they canceled out, right? So that this definite integral was going to have a net area of 0. So if you can recognize that the integrand is an odd function, and your limits of integration are need to be right so that you have that symmetry so that the net area is 0, then you can just quickly identify the definite integral as 0. So let's look at an example. X cubed plus x to the 4th tangent x. So I'm from minus pi over 4 to pi over 4. So notice that this interval, I have this pi over 4 units to the right of the origin and pi over 4 units to the left of the origin. So this interval is just right. And that this is an odd function because x cubed is odd. And x to the 4th tangent x is odd because tangent x is an odd function. And we can prove that here. Since minus x to the 4th power is always just x to the 4th, and tangent minus x is minus tangent x because tangent itself is odd, I get that this entire function is an odd function. So because it's symmetric about the origin, I know that the answer to this is 0. So with odd functions, if the interval of integration is right, it's nice that the solution's just 0. So it's not quite as handy with even functions because remember that the symmetry of even functions tells us that the value of the definite integral on an interval that is symmetric about the y-axis is double the integral from the y-axis to the upper limit. So for example, look at cosine, the integral of cosine x dx. Cosine is an even function, and if I look at it from minus 2 pi to 2 pi, I have the same distance along the x-axis to the right of the origin as to the left. So I can say that the definite integral from minus 2 pi to 2 pi of cosine, there should be an x there, cosine x dx is twice the definite integral from 0 to 2 pi. So that's not as handy as odd functions because with odd functions you don't have to do any work. You say, oh, the definite integral is 0. Here with even functions you do still have to find the antiderivative just on half the interval. So in summary, the substitution rule can be it can be fun to use in the sense that you might need to try a couple different substitutions. Often the inside function of a composite function is a good candidate. And remember, you need to get every part of an integral in terms of your new function u. So the dx and every factor needs to be in terms of u. And also with definite integrals, don't forget to turn the limits of integration into terms, put those in terms of u as well by evaluating your substitute function u at the original limits of integration.